Okay, so we're back. You should have available for you some slides for chapter 14 now out on my GCC, so you can pick those up, follow along today. Um, let's go ahead and finish up what I was going to do originally, and I wanted to take a look at a problem using ChemSep. And so just to kind of review that, I wanted to actually do this example that we had done previously, where we were doing extraction of acetone from water. And this was in our chapter 13 presentation. And we went through and we solved this problem originally. Let me scroll down here just a bit. When we went through this one, we made some assumptions that I gotta get the right problem here. Too many papers. This was the chloroform problem. Hang on. Let me get down maybe to the right problem. That might help here. I wanted, hang on. Let me see which one it is. Yeah, it's a little bit further on, so let me get to page 14. This is the problem I wanted. I wanted the acetic acid problem. Acetic acid, water, and butanol. And we had solved this problem previously, assuming that the water and the butanol were immiscible with each other. And that enabled us to go through the analysis. We'd looked at also the fact that that's not really the case. There is a certain amount of miscibility between water and butanol. There's still a two-phase region, but there's a certain amount of miscibility. And we'd looked at that, I think last time we'd taken a look at that. Let's go ahead and do this then in ChemSep. So let's go ahead and open up ChemSep. And we're going to treat this acetic acid water butanol system. And so once you've got it opened up, you can go ahead and enter in those three components to start with. And so once we've done that, then let's go ahead and look at types of operation that we're going to carry out. And so in our case, we're going to use a simple extractor. Although it's not the simplest problem that we can do, because in our original problem, let me just flip back over to it for a moment, we had, in this case, essentially two streams that we were bringing into it. Well, let me back up. The way to look at this is that in addition to a feed stream here of acetic acid and water, we have a solvent stream that's pure butanol and a second solvent stream that has some butanol with acetic acid in it. So in a sense, we're feeding in the butanol in two places in our extractor. Okay. So that means that when we set up our simple extractor here, to do this, when you first come into it, when you set up a simple extractor, it's going to show 2 feeds. In our case, we're going to have a 3rd feed because we have 2 places where we're putting in the butanol. Now, we had done some calculations with this previously in which we had, I've lost my page on this, so I can get to it. We went through an analysis on this and ultimately ended up estimating the number of stages that were required. And I think when we did that, we came up with something over 15, essentially 16 stages before. So we'll go ahead and we'll put that in, at least to run this case, an example with this. And then the optimum feed stage was somewhere around 12 from the top. I think I'm going to put it right around 13-ish in here, right? So that should set up your column for us, or I shouldn't say, it's represented here as a column, but it's really our extractor. Let's go to properties. This is where the tricky part comes in. Thermodynamic properties are the challenge with some of these problems, and in some cases it's more difficult than others. There's a lot of possible thermodynamic systems that we have available to us, but not all of them will be able to handle the specific components that we have for this extraction problem. So I'm going to choose a thermodynamic model that has K value with gamma. I'm going to choose the activity coefficient as this Uniquac C, and I'm going to choose ideal. And then we're going to load from this Uniquac file here, the one with the P at the end. And that should load in some values for our system. So everybody with me so far? Good? Okay. All right, so we've got that. Physical properties, we'll use default models. Reactions, there's nothing to do. Feeds, now this is where we have to, if you start playing around with the use of ChemSep and running extractors with this, you'll learn something interesting about this. We have 3 feeds. The feed at the top, right? We're numbering from the top down, essentially, in our extractor. Should be what feed? What do we have? We have water and we have 2 butanol streams. So which should the top one be? Should be the water, right? Why should it be the water? It's more dense, right? So you want to feed the dense one in from the top and the less dense one in from the bottom, so you get countercurrent flow on these things, right? Okay. So for that particular stream, let me see if I have it here. I can tell you what it was, and we can talk about it. That particular stream was 1.2 weight percent of a 100 kilogram per minute stream. Just to simplify things here, one of the first things that we'll do is we're going to change this to mass flows from molar flows. Okay, so make sure you have it on mass flows. You have to specify the type, so it's going to be split, which means, yeah, we'll see it'll come in a moment. The state will go with temperature and pressure. This column operates at atmospheric pressure, and we're operating at a temperature of, well, I guess technically speaking, in our example, we're at 26.7 degrees C, and I guess I didn't put that in, I just put in 25. But I just wanted to show you representative of what we are. And then for the flows that ChemSep wants it in terms of kilograms per second, we could convert that over. Just to make it simple for us to put in numbers for right now, let's assume it's on a 100 basis for feed 1 for us. And so if it's 1.2 weight percent acetic acid, then we'd have a flow of 1.2 and then 98.8. We have another feed. I'm going to jump back here to the operation here. I have a feed here. It's called feed 3 coming in around stage 13, at least to start us off with. That feed is the feed that has acetic acid in the butanol. And we're told that one has 0.4 weight percent acetic acid in it, and that the flow is 30 kilograms per minute. So if we use that 30 as our basis, 0.4 times that gives us 1.2. And so that means then that the remaining part should be, or excuse me, 0.12. It's 0.4 weight percent. So 0.12. And that means then that we should have a butanol flow of 29.88. Okay. And then our last one is the pure butanol, which comes in at the bottom. So it was 44. And if you set up this originally with just split, you'll find that ChemSep is unhappy with that. And it's going to expect for this particular one, which comes in at the bottom, that the split is below for it. So we need to specify it that way. Specifications, analysis, pressures. We'll go with constant pressure and atmospheric. Heaters, coolers, we'll assume that there's no heat loss from the column, right? Efficiencies, we'll leave at 1 for us. Column specs are fine. And if we've done all that and we've done it all correctly, we should be able to run this. So when we run this, we get some results. Everybody's work or trying it? So we get some results, and I'm going to take a look at mass flows and mass fractions. Now, the results that we have here are going to be slightly different than the results that we calculated before, just because of, one, the thermodynamic system that we're using, and two, the fact that we have some partial miscibility. What I want to look at, though, with this is rather than looking at streams, for instance, let's go and let's look at temperature, pressure, flow profiles. And when it comes back with the flow profiles here, does it two ways. It does it on a molar basis and a mass basis. We're considering everything here on a mass basis. So let's get down and look at this for a moment. I want to try to just to have you kind of interpret what we're seeing here. So you see that there's a light and a heavy, right? And that's kind of the countercurrent flows going through the extractor. Notice what happens. We're coming in with a feed at the bottom that's pure butanol, for instance. Because of there's miscibility of water into butanol, equilibrium right as you come in to the extractor right there means that there's going to be a significant amount of water that's going to go over into the butanol stream. So notice what happens here. Immediately the light stream here jumps by what? 12 kilograms. Oh, whatever our units are in this case, 12 kilograms per second. So And that's because of the water going into that stream. So it's reached equilibrium with the other stream, which is water plus some butanol. But because there wasn't any water to begin with in the butanol stream, the net mass transfer is going into that butanol stream. Right? So if you look at what's happened to the heavy stream has suddenly decreased by that same amount. Right? It's dropped by something on the order of 12 in this case. Yeah.
I thought that the water and the butanol were immiscible.
I don't have it up, and I should have done. Remember we looked at those ternary phase diagrams?
Yeah.
They were triangular shaped, and there was a region down at the bottom,
Oh, the
two-phase region, but it didn't extend. It doesn't extend all the way to 100% of either one. And in fact, in the one case, there's a pretty significant miscibility over here, and there's some miscibility on the water side as well. And it's that portion that's showing up here. Does that make sense for you?
So in a two-phase region, that's where they're completely immiscible. They don't mix at all.
Right. So this has come to equilibrium now, such that you do have these two streams at either end of a tie line, essentially, in there within the two-phase region. But the stream coming in, remember, was pure butanol. So in order to reach equilibrium, there has to be some water that has to go into that stream to have it reach an equilibrium state with it. Okay? Now, if you go up to the top of the column, right? The top of the column, or the extractor in this case, what are we feeding in? We're feeding in the water acetic acid system, right? No butanol in it. So notice what happens there. That's our heavy stream. As soon as we add that in, the stream that's going downward, our heavy stream that's going downward now, has jumped up. It went from 100 here to what? Something like 107. Why is that? Because equilibrium demanded that a certain amount of butanol go into that phase, such that we have, again, equilibrium between those two phases. And notice what happens to the light phase going upwards, right? It has a loss by that same amount. So you can see this kind of graphically. If you pull up under graphs and look at flow profiles, you kind of see these jumps. It's listing these things as L and V because it does it in terms of distillation. It's really doing an extraction problem here. But it's giving us a representation of how the flows change as it's going through the extractor. And you can see those jumps that are occurring in our system. So again, this is a little bit more, in a sense, realistic. You do have to worry about what thermodynamic system to use and whether you can find a good one that works for your system. But at least now we're taking into account this idea of partial miscibility that can occur in these kinds of systems. And it's kind of dramatic, I mean, that you see this happening when you look at the flow profiles. And of course, the numbers that we actually get are slightly different than the ones that we found in our example problem. But I'm not surprised, obviously, because the thermodynamics are different. And big difference here between assuming immiscible and then partial miscibility that we're accounting for. Okay. Questions, comments about that? All right, then let's go ahead then and jump into the next chapter here. So the next chapter we're going to treat is washing and leaching. So we need to define these two operations. In general, let's talk about what leaching is. Leaching is whenever you have some sort of a solid and there's a solute associated with that solid, and you want to remove that solute. Okay, so we say here it's leaching is essentially extraction of a soluble solute. Again, it's done typically with selective dissolution from an insoluble solid using a liquid solvent. Okay. This is an operation that's carried out pretty frequently in a variety of different ways. Some really simple things that we can think about are maybe coffee from ground coffee beans, or tea from tea leaves, or things like some oils from various types of foods and so on, like soybean oil from soybeans, peanut oil from peanuts. Another really big one is sugar from sugar beets, right? But it also shows up a lot in processing minerals, a lot of different places. I'm not making this an exhaustive list, but gold from gold ores, but there's all kinds of other minerals that are done using these kinds of systems. When you do this, the soluble constituent, whatever that is, can be solid or liquid. Sort of depends upon how it's, we'll talk about that, how it's associated with the solid. The soluble constituent in this case can be incorporated within the insoluble solid, could be chemically combined with it, or it could be, in a sense, mechanically held within maybe pores in the solid structure. So that's a case where maybe that could be a liquid. You might have a liquid maybe that's in the porous part of maybe some solid particles, and you're trying to get that out. So these leaching operations, similar to what we've done with a lot of other processes, can be done on either a batch or continuous basis. Yeah.
So for like the coffee, is it pulling out liquid from the coffee, or?
No, in this case it's not. What are you pulling out? You're pulling out all the components that you want for your coffee, right?
Right.
I mean, that includes the caffeine that's in there and whatever else is in there, that, you know, all the flavors and so on that are coming out with
So
it.
then what's left in the ground after you pull that out is just
A solid.
bean that's not even, that has pretty much nothing now, doesn't help you.
Well, it has a significant amount of those components leached out of it, right?
Right.
I mean, it depends. When you say, is it completely out? Well, that depends upon the thermodynamics and the whole operation that you're carrying out. How effective you are, right? To what extent have you carried out that separation? Yeah. Other questions about this? Okay, so we have a general idea what leaching is now. Okay. Washing is distinguished from it. It's sort of a special case of leaching. This is in general removal of what we're going to call here an interstitial liquid by another with which it's immiscible. Now, I know that sounds kind of convoluted, so let me see if I can maybe explain that a little bit better. In washing, typically what you might want to do is you might want the solid, and there might be something associated with that solid via upstream processing, whatever it may be, that there's some sort of liquid around it. Maybe you want to get rid of just that liquid, or maybe that liquid that's surrounding it also contains something else that you want to get rid of. And so what you want to do is you want to treat these solids with some other liquid that's going to then remove that component that you want to take away from the solid. Okay. All right, so that's why it's sort of a special case of leaching. And we'll see it's kind of a simpler case as we go along here. Okay, so washing of solid particles with a liquid. We're going to have to define some new terms here. One term that we're going to use is that the liquid with the entrained solids is known as the underflow liquid. Typically, it's removed from the bottom of a unit, right? So we carry out some sort of separator system. There's a lot of different types of equipment that can be used for these kinds of operations. Some of them are pretty sophisticated. For now, let's just do it sort of conceptual for us. The liquid with the dissolved solute is known as the overflow liquid. Okay, so we're going to keep those terms, and we'll define some symbols for them coming up here shortly. And that's removed from the top of our separator. So what we're now going to do is we're going to define some basically concentrations in a sense. So we'll say that Y is equal to the solute mass fraction in the overflow. Sorry, so that's coming off the top. And X is the solute mass fraction in the underflow, coming off the bottom. So when we carry out a washing operation, we're essentially exchanging liquid. Right? That's all we're doing. We're kind of sort of exchanging liquid. As a result with this, in many washing operations, at equilibrium, the solute concentration in the underflow liquid equals the solute concentration in the overflow liquid. And as a result, then we have essentially that Y is equal to X once you've hit equilibrium. So one, we're gonna look at a case here coming up, but one case, here's a simple example maybe to think of. Maybe somebody's dug up sand from the ocean and they want to use that sand someplace else. What comes along with the sand from the ocean? Seawater, right? The sand is wet and it has a lot of seawater on it. What's in the seawater? Salt. We don't want salt on the sand, so we want to get rid of it. So we're going to carry out, let's say, a washing operation. So what are we going to do? Well, we're going to bring in pure water, right? We're going to mix it up, and we're going to let the particle stream come out the one side. We're going to take off the water off the top side. And essentially all we've done is we've come to an equilibrium point where the amount of salt in both the underflow and the overflow is going to be equivalent. Right? If we're carrying this out as an equilibrium operation, that's what's going to happen to it. Okay. So that's why we have this expression. Oh, let me just do one other thing. So certainly, we can do this on a single batch basis. We can start to do it also then on a continuous basis or a counterflow type basis. And so at the bottom here is a schematic showing a case like that. We are going to use capital U to represent underflows and capital O to represent overflows. Right? And so this is kind of similar to a lot of other operations that we've done, with absorbers and strippers and so on, in terms of our notation and so on. Right? So we use X with the underflow, Y with the overflow. You see here a countercurrent operation. This one's showing various stages. All right. So a lot of what we've learned is going to apply here. So we can make some pretty direct analogies to what we've done previously with absorption and stripping and so on. And carrying it further, really looking at liquid-liquid extractions. So washing. We're going to make some assumptions here. The assumptions that we're going to consider here, that we have essentially constant fluid and dry solid densities. The solute-free solid is insoluble in the solvent, so we're not getting rid of any of that. No solvent dissolves into the solid. The solute does not, in this case, I'm going to use this term, and we have to be careful about this, adsorb. So what's adsorb mean? Adsorb means that you have something that's associated with say a surface or something like that. Comes up and wants to stay in contact with it. Okay. Solute does not adsorb onto the solid. Negligible heat of mixing. No solid is carried with the overflow fluid, and the solid porosity is a constant. With those assumptions, then that means ultimately that we can have constant overflow and underflow flow rates. That's nice. And as a kind of rather direct analogy to what we've been doing previously, we can write an operating line, which looks very, very similar to what we've done. In this case, we have a slope of U over O, and we have an intercept here, yn plus 1 minus U over O times x sub n. It looks very, very similar to what we've done previously here. Which means that under these conditions, we've got an operating line which is straight. It's a washing situation, which means that our equilibrium line is straight, which means that we can then do McCabe-Thiele on these. But in addition, McCabe-Thiele isn't quite as limited. We can actually go ahead and use the Kremser equations. So Kremser applies, and so we can do analyses that way. When we talk about washing, because sometimes what we're trying to, let's say, remove might be contained within pores, let's say, within the solids, and we have to consider porosity of the solids. And so we're going to define porosity, which really means the void fraction. We'll define it as epsilon. And that's the volume of the voids divided by the total volume of the particle system itself. So we can use that to then describe, let's say, volume of liquid divided by total volume of underflow, or volume of solids divided by total volume of underflow. We can then define the underflow flow rate. That's our capital U. And we oftentimes will do this on one of two bases. One basis is that we do it on the basis of the rate of dry solids, because that's a constant, right? It's not changing the dry solids in any fashion. So we can then express this underflow rate in terms of the rate of the dry solids, some time basis. Another term that gives us the effect of the porosity on it, and another term that it gives us the effect of densities here, right? So rho F is the fluid density, and rho sub S is equal to the solid density. Sometimes it's also done in terms of the volume of the so-called wet solids. Under those conditions, then, we can write that the underflow rate then is given in terms of some porosity and some fluid density force as well. Okay, so let's go ahead then and work on a problem. Let's suppose that the setup is that you're working on a new glass factory near the ocean. So you're going to use sand that comes from the ocean, from a beach. Carries with it seawater. Seawater has a certain amount of salt in it, and you want to remove that. We're given some information here. The density of water will assume to be 1. The dry sand, if you just take the sand and account for all the voids within it and so on, has a certain density. And then of course there's a density for the dry sand if you were able to, let's say, crush it so that there was no pores, and that would leave you with just the solid density, right? And that's going to be higher. And so that's what we see. So what we want is we want to come out of this process with a sand that has entrained water that only has 0.2 weight% salt in it. And we're told here that for each 1,000 cubic centimeters of wet sand feed or fed into the system, you use a 0.5 kilogram of pure wash water. So in a countercurrent washing process, how many stages would be required to carry this out, and what's the outlet concentration of the wash water? Okay. Let's I guess what we could do is we could sort of set up what our system looks like here in some fashion, right? So we've got some sort of a system here. We've got coming in here U naught, X naught. Oops, I got that going the wrong way. And then we have coming out in this countercurrent configuration, we've got O1, Y1. And that means coming in over here, we've got O n plus 1, Y n plus 1. And coming out, we've got U sub n, X sub n. And we'll assume that we satisfy all the previous assumptions for treating these washing type problems. So where do we go to from here? In order to evaluate this problem, we could do this two ways. We could do McCabe-Thiele, or we could do a Kremser method for this. Let's start with, let's do McCabe-Thiele, okay, to begin with. So right off the bat, with this washing system, what do we know about equilibrium? What's the equilibrium for us in this case? Any one of the given stages in there, what has to be true about y and x? Y equals x. So that's our equilibrium line. That's a simple one. Okay. So then we need an operating line, right? What does that mean that we need then? That means that we need the underflow and the overflow. And for our system, given our assumptions, those values are going to be constants through the system. So we need both of those. Can we get them or some measure of them, or even maybe the ratio of them, for instance? Well, let's try to work on this. What do we know about this? For 1,000 cubic centimeters, cc's, of wet sand, we use a ½ kilogram of pure wash water. So what is that value related to? Not quite yet. But if we're putting in a ½ kilogram of wash water for each 1,000 cubic centimeters of the wet sand system coming in, that ½ kilogram of wash water coming in is what? Is actually the overflow. Right? That's the pure water that you're feeding in, and that has to be constant going across the system, right? So this is associated with the overflow. How about the underflow? It says here that for each 1,000 cubic centimeters of wet sand fed, they use this much, but we also know up here that this system contains 40% by volume seawater. So for 1,000 cc's at 40%, how much water do we have?
400.
Which is 400 or 0.4 kilograms, right? So 0.4 kilograms is associated with the underflow. So right away, we know then that in this case, U over O is equal to 0.4 divided by 0.5, which is 0.8. In our process, what do we know about some of these quantities? Do we know X naught? What's our solute in this case? Salt. So X naught is? Yeah, 0.035. Okay. Do we know X sub n? It's what? 0.002. We know y n plus 1. 0. So the only, from an overall picture here, the only concentration that we're missing is y1, right? About a mass balance. Right, so we could do a mass balance. And it would say something like O times yn plus 1, that's going in, right, plus u naught times x naught, right, is equal to O1 y1, or just O, right? I don't really need a naught on these. Probably should get rid of those, because they're constants in our problem. So this is O plus u times x sub n. This term here goes to 0, right? Because of yn plus 1 is 0. So we can readily solve for y1 equal to, in this case, then it's going to give us what? U x naught minus times minus x sub n over O, right? And you can substitute in values for this. If I did that correctly, this should give us a result of 0.0264. And so as soon as we have that, then we can immediately write down what the operating line is. So our operating line is, and we'll stop with this, our operating line is y is equal to u over O times x plus y in, which is y n plus 1, minus u over O times x out, which would be x sub n. And this term here is 0 for us, right? So we've got our operating line. And so, again, with equilibrium line and operating line, you can plot them up on a plot. We've got a straight lines for both the equilibrium and the operating line, and you can step off stages. And when you do that, you get something like 1, 2, 3, 4, 5, 6, and this is about roughly a half. So about 6.5 stages-ish. Then you should do it. Okay. All right. That's pretty much all we've got time for today. We will kind of wrap this up on Monday. We'll finish off this problem. We'll actually do it with the Kremser method as well, just so that we've done it that way, and kind of wrap things up. Okay? So have a good weekend. Don't forget about the homework.